All right, hello everybody and welcome back to video number 7 for regression analysis. This week we're going over chapter 6, which talks all about transformation of variables. So for just a little introduction, transformation of data is often done so analysis can be carried out. This is done to ensure linearity, to achieve normality, and to stabilize the variance. So transformation is necessary when the model of the original data violates at least one of the standard regression assumptions that we spoke about in a previous video. These are examples of linear equations since beta sub 0, beta sub 1, and beta sub 2 enter linearly, as this is not a linear model right here. So our ones on the left right here are our linear models since beta sub 0, beta sub 1, and beta sub 2 enter the model linearly. And then the one on the right here is not a linear model since our beta sub 1 does not enter the model linearly. So transformations may be necessary for the following reasons. The relationship can be non-linear. So we have this equation right here, which states that it is not linear. This is non-linear, but if we take a logarithmic of both sides, we can get a linear model. So our one on the top here is not linear, but if we take the log of both sides, we obtain a linear model. The next reason could be that the response variable may have a probability distribution related to the mean. So we can transform the data here to ensure normality and the consistency of error variance. And the last reason is we can examine the residuals and then determine if a transformation needs to be done. So we can examine these residuals by looking at the scatter plot and determine if we need to transform the data or not. So next we're going to move on to section 6.2. 6.2 talks all about the transformations to achieve linearity. So relationships can be non-linear, but in some cases, simple transformations can be done to obtain linearity. So a linearizable curve can be determined when observing the scatter plot of y against x. So strictly non-linear models require different methods of fitting, which we're going to discuss in a later video. So now we're going to move on to section 6.3. This gives us an example of transformations using a study done on bacteria deaths due to X-ray radiation. So they are testing marine bacterium following exposure to 200 Kelvin of X-rays. So the response variable in this case would be n sub t, which is the number of surviving after the exposure times t. So n sub t and t should be related by this equation right here. So we have our n sub t is equal to our n sub 0 times e to the beta sub 1 times t. And since we're dealing with time here, t always has to be greater than or equal to 0. So our n sub 0 and our beta sub 1 are parameters. In this case, n sub 0 equals to the number of bacteria at the start of the experiment. And our beta sub 1 is our destruction rate. So we can transform the model to get this equation right here. So we have our transformation, which is n sub t is equal to n sub 0 times e to the beta sub 1 t times our epsilon prime t. So we have our inadequacy of a linear model. So our beta sub 0 and our beta sub 1 are constants, and our E sub t are our random errors with 0 means and equal variances. So if you look at this plot on the right here, we can see that we lose linearity as t becomes greater. So we see kind of a little pattern between 2 and 10. And as we start getting greater than 10, we see a pattern that is different than this. So we can determine that at around the time of t equals 10, we start to lose linearity. So the plot of the ln of n sub t against the t appears linear, which indicates that the logarithmic transformation is appropriate for this data. So they showed that they transformed the data into a logarithmic transformation, and this indeed did satisfy that we did achieve linearity. So this is a good real life example of how we can have accurate data, but that data might not achieve linearity like we would need it to. So although we have accurate data, we might need to transform some of it so we can further use that for analysis. So just like we've talked about in the past, they have showed that this plot is indeed random. So therefore, it is a good plot overall, the logarithmic plot. So we can tell that the model is indeed a good fit, the logarithmic model, not the original model that we had. All right. So now we're going to move on to section 6.4, which are the transformations to stabilize variance. So transformations can also be used to make the variance constant for all observations. This is our homoscedasticity assumption. So like we talked about in previous classes and videos, bad graphs tend to show a funnel shape or some sort of shape or pattern or something like that. So if this occurs and no fix is done, then we would have a false sense of accuracy. So whenever we see a graph like this, we do need to make some changes or transformations to our data in order to achieve the randomness that we need. So one property with normal distribution is that the mean and variance are independent of each other. So we can have a binomial and Poisson distributions, which are great examples of this. So when the relationship between the mean and variance is known, simple transformations can be done. Now, the book looked a little bit about some data referring to injury incidents in airlines. When they looked at this, the residual plot, homoscedasticity was violated since the data seems to behave like a Poisson distribution. So they then used a square root transformation, which yielded a valid residual plot. So we had a logarithmic transformation before, and now we are seeing in a different example that square root transformations can also be done, which help us achieve the same thing which we need, which is linearity. Most Poisson distributions can be transformed using square roots. So this is just a good thing to keep in mind, that if we are ever dealing with a Poisson distribution, we can always try the square root transformation, and that will most likely yield us the answer that we need. Right, so section 6.5 is going to talk all about the detection of heteroscedasticity errors. So the residual plot consists of if the residual plot consists of two parallel lines to the x-axis, then there is no evidence of heteroscedasticity. A plot of standardized residuals against the predictor variable can lead to the presence of heteroscedasticity errors. So we do not want heteroscedasticity errors in our data set. So now section 6.6 is going to talk about all about how to remove those heteroscedasticity errors. So heteroscedasticity errors tend to occur when unequal variances are encountered, that the standard deviation of residuals tends to increase or decrease as the predictor variable increases or decreases. So if the standard deviation increases, then and the predictor variable increases, then that's when we tend to have unequal variances or when they both decrease. So they both have to be going in the same direction for this. So we have our variance, which is indicated by the formula up on top right here. Our variance of the errors is equal to k squared times x sub I squared, and our k is always going to be greater than 0. So if we look at the information in the middle here, we can define a new set of variables and coefficients to work with. So we have our y prime, which is going to be equal to our y over x, our x prime, which is going to be equal to our 1 over x value, our beta sub 0 prime, which we're going to equal to our original beta sub 1 value, and our beta sub 1 prime, which we're going to equal to our original beta sub 0 term. And then we have our epsilon prime, which is going to be equal to our epsilon over x. Also, if you look down below here, we have our y sub I prime is going to be equal to our beta sub 0 prime plus our beta sub 1 prime times x sub 1 prime plus epsilon sub 1 prime. So this right here is just taking all of our new variables and putting it into a linear model. So the residuals from the transformed model against the predictor variable indicate a rough band parallel to the x-axis, which indicates that there is no evidence of heteroscedasticity and that our transformed model is accurate. So if we yield a residual plot with a rough band parallel to the x-axis, so we have all our data kind of in a line parallel to the x-axis, then we can conclude that there is indeed no evidence of heteroscedasticity. So section 6.7 is going to talk about all about the weighted least squares. So linear regression models with heteroscedastic errors can also be benefited by the weighted least squares method. So parameter estimates are obtained by minimizing a weighted sum of the squares of residuals, and the weights are inversely proportional to the variance of the errors. So we can use this formula right here, which is the summation of 1 over our x sub I squared values times our y sub I minus our beta sub 0 term. And we're going to subtract the beta sub 1 term times the x sub I term. And then we're going to square that whole thing. So this is just a little introduction to the weighted least squares, but we are going to dive more in depth into this in a future video. So just keep this formula in mind right now. We're going to do a little work with it in this chapter, but we'll worry about it more later. All right, so our section 6.8 is all about the logarithmic transformation of the data. So we did see the logarithmic transformation done in the bacteria data before, but now we're going to talk more generally about what exactly to do to transform the data logarithmically. So this is the most widely used transformation. This is very useful when the variable has a large standard deviation when comparing that value to the mean. So we fit this model right here, which is ln of y sub I, which is equal to our beta sub 0 term plus our beta sub 1 times our x sub 1 plus our epsilon sub I term. So the residuals suggest a more appropriate model. This is a multiple regression model, which can be used to help detect model deficiencies. So that multiple regression model would be our ln times y sub I, which is equal to our beta sub 0 term plus our beta sub 1 times x sub 1 plus our beta sub 2 times x sub I squared plus our epsilon. So the only difference from this equation right here is that we are adding a term of beta sub 2 times x sub I squared. So that so this right here is a simple linear regression term, and then the one I just explained about adding the beta sub 2 term is going to be our multiple regression model. So section 6.9 is going to talk about another type of transformation, which is the power transformation. All the previous transformations that we have spoken about so far can be classified as power transformations as a whole. So power transformations is the big term for all the transformations that we would do. So the logarithmic and the square root fall under the power transformation category. So we would raise the response variable y and or some predictor variables to a power. So we can see that the ladder of transformation can be done, which a ladder of transformation is numbers chosen to easily interpret. So some of the numbers that the examples in the textbook have shown are -1 and 1 and 0 and a half and -half, just some easy numbers that we can visualize ourselves, which help us to easily analyze the data and get a bigger picture of the data. So this in the book is shown in the example, which compares the body weight of a species to its brain weight. So they used lambda equals 0, a log transformation. They raised both variables to the same power, but in other instances, the variables can be raised to different powers. So in this one, they kept it simple and raised them to both powers. But in real life, this doesn't have to occur this way. You can certainly raise the variables to different powers to achieve the analysis that you need to achieve. All right, so section 6.10 in this chapter was just a summary of everything that we talked about today. So residuals should be examined after fitting to determine any evidence of heteroscedasticity. This occurs when the residuals tend to increase or decrease with the values of the predictor variables. Like we saw, this can be removed by transforming the variables. The residuals from the transformed models should indicate no evidence of heteroscedasticity. So those are some big takeaways from today's video and chapter number 6. Thank you guys so much for watching. If you have any questions or comments, feel free to write them in the forum, and see you next week.